All right. In 7.4, we're going to move from, how do I say it, simplifying expressions to solving equations. Now, the big idea here is we now have a left and right hand side. So, just real quick, what do I mean by that? Well, if we take a look at everything we did in 7.2, for me just a second ago, but for you whenever you're watching this, notice this question doesn't have an equal sign. I'm drawing the equal sign to say this is equivalent, this is equivalent. So no equal sign, no equal sign, no equal sign in the initial problem. But now we get to 7.4 and there is an equal sign. Now that actually, I mean, there's still going to be some hard work here, but it's really going to make the majority of our life easier because now we have a left and a right hand side. And so rather than forcing ourselves to make common denominators everywhere, we can rather just get rid of denominators in step one. And sorry, just quick catch, this should be a z, and I'll reiterate that when we do it, but that should be a z just early on before we're stuck in the math. But we learned early on that if I can identify the least common denominator, and if we look, what could all of these denominators divide cleanly into? The answer is 12x. If I multiply that LCD, fractions will be gone everywhere. Let's see how. 12x over 1 over 3 over 2x, times 3 over 2x minus 4 over 6x. I guess I could have reduced the 4 and the 6, but oh well, it'll work out just fine. And maybe I'll write it like that. Why not? Now notice again that I just have, again, 12x over 1. That's all I'm dealing with. Now when I distribute this, hear this carefully, the 12x and 2x will reduce to just 6, but the 6 will multiply to the 3 left over, giving you 18. 12x over 6x will reduce to 2, and 2 will multiply the remaining negative 4 and give you negative 8. On the other side, 12 and 12 will reduce, so we just have 5x. And believe it or not, that's the heavy lifting for that problem. That leaves us with just 10 equals 5x. And so x equals 2 by just dividing at the end there. Great, not too bad. The bad one, and I will say again, this is the most similar to your exam question, will look a lot like this one. It's a lot of work, but remember there's only one crazy question like it, but we'll warm up to it as we keep going. Up next, my least common denominator. Actually, this one's easy because I see z minus 5 twice, because again, that's a z. Catch that typo. And so, if I multiply z minus 5 everywhere, let's see what I get. First, it looks like that because I have to multiply it everywhere, the entire left side, the entire right side. And I'm multiplying z minus 5 technically over 1, and z minus 5 technically over 1. And when I do that, also maybe it might be worth writing out that the 2 is actually technically over 1. And so let's multiply this. Z minus 5 over z minus 5 cancels, leaving me with just 8. Z minus 5 times negative 2, careful, I've got to distribute that. That'll make a negative 2z. That'll make a positive 10. And then on the right hand side, z minus 5 and z minus 5 cancel totally, and I'm just left with a z. If you work that out really quickly, if I add the 2z to the other side, I'll be left with 18 by also combining. And I've got 3z. So again, I'm just taking the 8 and 10 and putting them together. I'm adding the 2z over and getting 3z. If I then divide, I get z equals 6. So nothing too bad there either. So really, the name of the game here is, since I have an equal sign, I can eliminate fractions in step 1 with some careful distributing. That's the hard part, the careful distributing, because again, we got a 2z and a plus 10. Careful about that. But besides that, we turned some very ugly looking problems into some very easy problems. Now there is one caveat though that we need to say early on, in that it is that there are chances of creating what we call extraneous solutions. Solutions that come out from correct algebra but don't work in the final problem. Now, what you should do is you should take this answer and plug it back in and check. Take this answer, plug it back in and check. But I'm going to say, and you should check for other possible things that just might happen, but for the most part, 90% of the time, as long as when you look at this answer, if you ask yourself, would this make 0 in the beginning of the problem in the denominator? So let me maybe say that again. If what you get in your answer would make 0 in the denominator of the beginning of the question, then that's when you know you have an extraneous solutions. But still, you should either way check and plug in and verify the whole result that it works out nicely. But for the most part, if it just causes 0 at the beginning, that's the problem. And we'll see if any extraneous solutions show up here. Hopefully you notice that b minus 4 is the common LCD. This time I'm just going to write that the LCD is b minus 4. And I'm already just going to go ahead and distribute it just to kind of save some time here. So the b minus 4 over b minus 4, when I distribute it, will cancel and just leave me with 3b plus 4. The b minus 4 over b minus 4 will cancel, leaving me with just b squared. And careful, the b minus 4 times 3 will leave me with 3b minus 12. So hopefully you caught that again, the b minus 4 just canceled on the left, so we had 3b plus 4. The b minus 4 canceled with the b minus 4, leaving just the b squared. And then the b minus 4 times the 3, since there was nothing on the bottom, the 3 distributed entirely to what I was multiplying. Okay, well now, here's the hard part. I've got a squared in my algebra I need to solve. What we learned in the end of chapter 6 is the only thing you can do once you have an exponent of 2 essentially in your problem is pretty much just move everything over to one side and try to factor. In other words, get one side to equal 0, because the zero factor theorem says that as long as you have algebra that's only multiplying, it's really easy to make 0 out of it. So we're going to move these two smaller terms over to the left-hand side, because everything else is mostly positive here. Let's see what happens. If I move those over, I'll still have just b squared, but a 3b and a minus 3b will just cancel, and a negative 12 and a minus 4, when I'm moving it over, will make negative 16. This is a very special result. I just made another difference of squares, so I've got b minus 4b plus 4. And what makes each of these 0? Well, positive 4 for the first one that I wrote, and negative 4 for the second one that I wrote. But here is the crux. Can these be plugged into the original? Well, if I plug in 4 into the original, I would get 0 in the denominator. And what I should do, so in other words, I know 4 isn't going to work right away. Stop, you're done. What I should do is I should be a good mathematician and verify that negative 4 works as well. But I've already done that together in lecture, and I know it does. But we'll say 4 is extraneous. Negative 4 is valid. And maybe just saying that wording is hopefully encouraging you to say, you should plug in both. Well, I guess you should try to plug in both, but you should realize 4 makes 0 on the bottom right at the beginning, so stop, don't go any further. This negative 4, you're going to have to spend some time simplifying and seeing why it is actually valid. But it is, trust me. All right, we're here for the last big, ugly problem here, and let's see how it goes. Oh no. The issue this time is that we have two distinct kind of, we would call them linear terms in the denominators. We have two distinct different types of kind of factors, so to speak. And the only thing I can do to eliminate fractions is by multiplying the entire LCD. And so the entire LCD, unfortunately, looks like this. That's just my LCD multiplying to the entire left-hand side. I'm running out of space here. And to the entire right-hand side. Goodness. So, I know that looks awful, but hopefully you kind of see the idea there. Is I would have written that out entirely over there, still over 1. I just kind of ran out of space there for a second. So, I shouldn't have written that so big. That's why. Anywho, let's see what happens, and we got to be really, really careful here. On the left-hand side, the x plus 1s are on top and bottom. They will cancel. But I have a 2x minus 3 and a 2x minus 2 that was left over. On the next one, I've got a minus sign, careful about that, and the 2x minus 3's cancel, but I have an x plus 1 and an x minus 2 left over. Similarly over here, and I know I wrote it poorly, but there's a 2x minus 3 which cancels, and so there's an x and an x minus 1 that I just multiplied over. Again, it's the x plus 1 and 2x minus 3 multiplying to both numerators. The 2x minus 3's went away over here. The x minus 1 stayed and multiplied. Alright, as I was working, I caught myself in one little mistake, and that's that there's an x plus 1 on the bottom, and I had initially wrote x minus 1 up here, but that should be to make common. I wrote plus 1 here, but I forgot to write plus 1 here, so this should be a plus 1. This should be x squared plus x. So everything else so far is valid. This should be x squared plus x. Now let's see what happens. Goodness, that'll be 2x squared. That'll be negative 10x. And that'll be plus 8 equals 0. Finally, all that equals 0. And finally, we can factor and get x minus 4, x minus 1 equals 0. We get x equals 1 and 4. And you should plug both of those in and verify that they work. But for sake of time, and as you can see, I already had some scratch work verifying my results and eventually looked up and caught my mistake. But, you know, that happens sometimes, and there's lots of little things to do in this problem. This is the biggest problem that you're really going to see probably in this entire class, honestly. But the good news is it's just one of your questions on the exam. So although it's daunting in how much there is to do, it still is just 1 out of 26 percent on the exam. So be careful is the big thing. All right, from there, we now have kind of back to what we did in chapter 2. Let me try to focus this. Hello. That didn't focus it. There we go. Back in chapter 2, we kind of learned to solve for a variable. Now, this is going to get more complex in this section because the variable I want to solve for is in the numerator and denominator, and it's not really going to factor out nicely. And so in this one, the first step is actually what we just learned how to do in the last few examples, which is multiply your denominator to get rid of it. So if I multiply t plus 5 everywhere, I get t plus 5 times v equals just 50t, because after all, I multiplied the denominator to get rid of it from the right-hand side. What can I do there? I can then distribute the v, so I get tv plus 5v equals 50t. Now what I can do is I can move things around and get my t's on one side, and I think the easiest way to do that would be to leave the 5v on the left and subtract that tv over. Now, this is where things get wacky. It's almost like it feels like a switcheroo, and it kind of is a little bit confusing about what the goal is. And so let's reiterate what the goals have been as I've been working through this. First, no one likes fractions, so multiply your LCD to get rid of denominators. Then you need to distribute everything so that your t's aren't trapped in parentheses anymore. From there, move everything over so your t's are on one side, and this is the really cool, clever trick that you might not notice or think to do at first. You can now factor out your t's since they're all on the same side, and you can just divide over that thing that doesn't involve the t anymore. And so there you have it, you've just isolated t. So again, the steps there are, again, first, no more fractions, no one likes them. Then distribute so that all your t's, or the thing you want to solve for, are freed out of their parentheses. Gather your t's on one side, doesn't matter which. Factor out your t's, and then divide the leftover things from your factoring. So pretty cool, interesting concept. The next one here, this is some sort of physics formula. We want to solve for d, and d is on the bottom, and so we're going to go through really the same exact process here. So we're going to multiply, and we got to be careful with all these f's. So as I multiply this denominator to move it to the other side, I'm going to distribute. So I've got capital F lower f1 plus capital F lower f2 minus capital F lowercase d, right? So I'm just multiplying that and distributing as I go, and all that's equal to little f1, little f2. All right. Well, like we said, the next step is move all the terms that only have the d to one side and move everything else to the other side. Now in this case, because it's like 2 against 1, I guess just the way I'm seeing it is I'd rather keep these two on this side and just subtract over little f1, little f2, and add over capital F lowercase d. To me, that seems like the easier move of getting the terms with d on one side and all the other terms on the other. Well, from there, we're really pretty much done. You just need to divide capital F. So there we go. Capital F lower f1 plus capital F lower f2 minus little f1, little f2, all over capital F. Now, are there other ways you could maybe write that and deal with the capital F's on their own little terms? Yes, but really, that will be fine. So, great. We're finally there. We're at 7.5. We're really close to being done. We've got a few word problems, and then we've got variation to talk about. So, for 7.5, we've got kind of that similar word problem about how can people work together. And it's not too bad, but let's see what we can do here. It says one painter can paint an entire house in 12 hours. The second painter takes 8 hours. How long can they paint one house together? The trick here is when they tell you how long they can paint, T over 12 is the ratio for how long it would take the first painter to make one house, because after all, if you plug in 12, you get 12 over 12, which is one complete house. Plus the second painter takes 8 hours, so T over 8. They can paint faster. It only takes them 8 hours, 8 over 8, to make one whole house. And the question is, when will they equal one entire complete house? Well, once again, you guessed it, this goes by pretty quick. You're just going to multiply the LCD. Now, I'm going to actually kind of work to find the LCD here. The LCD of 12 and 8 is 24. If I multiply 24, the LCD, so maybe we'll write that. LCD is 24. If I multiply that 24 to both sides, here's what I get. I get 2t plus, let's see here, 24 over 8 reduces to 3, so 3t. And that equals 24. Really, I'm pretty much done there because that's 5t. So I get 24 over 5. And that's all there is to it. That's how long it takes them to paint a house together. Now, 24 over 5 is an ugly fraction, but the idea is it is faster than 8 hours. I mean, it's shorter than 8 hours. Either way, that's the same thing. And that should make sense because if they're working together, just kind of a check for your answer should at least be smaller than one of them working alone, because after all, they're both working together. Okay, from there, this next one is going to be pretty tricky. But the idea here is we're going to deal with rate equals, rate is distance over time. So a basic physics formula there. Or, in other words, your distance is your rate times your time. Or you could even flip that around, another way and solve for t. And you could say t is d over r. It's up to you how you want to mix that around. But, we talk about things as miles per hour. Miles is a distance, hour is a time, distance over time, that's your rate. Miles per hour is a rate because it's my distance, miles over how many hours it would take to drive it. How long have I traveled? Well, if I'm driving at 60 miles an hour for 1 hour, then I've gone 60 miles. If I'm driving at 30 miles an hour, maybe let me say it another way. If I'm driving at 60 miles an hour for 15 minutes, then I've gone 15 miles. There's kind of, a ratio. Sorry, what did I say? 60 miles for 15 minutes? Yeah. I'm trying to think of some other numbers. If I'm driving at 30 miles an hour and I've driven for half an hour, right, I'd only be going for 15 minutes. And so maybe you plug in those numbers and kind of just assure yourselves that those formulas are making sense. Now, from there, here's where things are going to get interesting. It says a sports car travels 15 miles per hour faster than a loaded truck. And then here's the big crux here. It says, in the same time, so interesting, I will need the other formula because time is the equality there. In the same time, the sports car travels 156 miles, the truck travels 120 miles. Find the speed of each vehicle. So we want the speed or the rate of each vehicle. Now, because time is equal in the same time, we're going to isolate t and set equal. So what do I mean by that? Well, if I look at this formula, to solve for t, it would be d over r. Right? I would just divide the r, and then d over r would give me t by itself. And so now what I'm going to do is I'm going to figure out this question like so. The sports car travels 156 miles. That's its distance. But I also know that the sports car is 15 miles per hour faster than the truck. So notice what I'm doing there is I'm saying the sports car goes 156 miles distance. The sports car's rate, and sorry, this is, I should use like capital T for truck or something to not be confused with like time. But capital T for truck, whatever its speed is, go 15 miles an hour more, and that's my sports car kind of fraction, my D over R. 156 over whatever the truck is plus 15. And I'm going to set that equal to, because it says in the same time, well, what the truck does. Well, the truck only goes 120 miles, but the truck's speed is, well, just T itself. Now, I think for sake of time, I'm just going to set this one up and maybe do the next step. I would multiply both of those unique denominators. I would need to multiply both of them. And by doing so, I would have gotten 156 capital T on the left, because I needed to multiply the t plus 15, which canceled, and the t also came over. And then from there, I needed to multiply the t plus 15 to the 120. And I technically multiplied the t as well, but it canceled itself out. And that would be your setup, and I'll just say from there, ... we continue. Okay. Up next, let's see here. Garth can row 5 miles per hour in still water. It takes him as long, interesting, so once again, that's a time measurement there. That's kind of confusing because long could mean distance as well. But it takes him as long to row 4 miles upstream as 16 miles downstream. How fast is the current? So once again, we have a D over R relationship because the time is equal. So the distance is 4 miles. Now what's the rate? And if you remember this kind of plane problem from a while ago, the rate would be his boat speed when he's going, upstream minus 5 miles an hour. So in other words, the issue here is when he's going upstream, he's going against the current, so however fast he's going, he has to subtract 5 in order to cover that distance. When he's going downstream, notice he obviously goes a lot farther and faster because now his boat speed is being added to you know what? Sorry, I flipped this all around. His speed is 5, and it's the water with him and against him. This is why we don't do math at 1 in the morning. So his speed is 5, and then, he's going against the water. His speed is 5, now he's going with the water. That was a close one. Okay, so let's just say that again. When you're in the plane or those plane problems, the idea is, again, it's you going with the wind or against the wind, with the water or against the water. So once again, Garth is going 5 miles per hour every single time. It's just that when he's going upstream, he can cover much less distance because the water's working against him. And then when he's going downstream, he's going with the water, so the water's going with him. It's adding to his speed. Okay. Similarly, we're just going to set this one up as the next step. You would simply distribute and get 20 plus 4W. Really, you're almost cross-multiplying here. You can get away with that, saying that terminology there. And then over here, you would get, I think that would be 80 minus 16W. And we'll just say dot, 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 because that's not too bad for you to take from there. But really, the main thing is in the setup. And what I want you to notice is both of them had this in the same time prompt. So both of them are doing this D over R relationship. Okay. The last concept we need to cover is variation. And we're only going to cover direct and indirect. I know there's a question about joint variation on the back, but I think you can tackle that one in your homework. It's just multiple joint or inverse variations, or multiple direct and indirect variations. Now, variation is an interesting concept, but it's really just kind of doing more of these kind of little formulas here. They're really small and simple, but the wording can feel kind of wacky. Also, the idea is there's a 3-step process to variation. But first, let's review the definition. If we say x varies directly, sometimes we say to or as, or directly to y, what that translates to is that x is equal to k times y. So the varies is kind of your equals sign, and almost varies is equals k times is the way you phrase it. And so the idea is there's a multiplying relationship here, and now we need to kind of just talk about what are the steps of variation. So the steps are write the variation formula. That's step 1. Step 2, sorry, I should say formula. Step 2 is substitute. That's what I was going to say, plug in. I was like, why was there a P? Plug in the initial info and solve for k. And now we're going to say rewrite the formula with k. And finally, plug in new info and solve. So we write the initial variation formula. So in other words, we're going to read somewhere that x varies directly to y, or x varies directly to y squared, and so now it's x equals k times y squared, or something like that. We then are going to plug in some extra information they tell us about. We're going to solve for k. We're going to rewrite this just with k plugged in. Then they're going to give us new information, and we're going to solve that. So they're all really simple problems, but I think a lot of times we get really stuck in these steps. So let's see them worked out a few times. And again, we're just going to do a direct and inverse variation, and they're really not too bad. So it says, suppose y varies directly as x. So great, y equals k times x. And then it says, if y equals 12 when x equals 6. So here's step 1, here's step 2, and 3. Right, we're only just reading from right there to right there. So step 2 and step 3, we have 12, we have now k times 6. So guess what? I now end up getting k equals 2. So now I've got y equals 2x. And so really, I mean, you can see how simple that was. It's just if y equals 12 and x is 6, well, plug in 12 for y and 6 for x, solve for k. I just divided the 6, I got 2. I'm now just rewriting this initial formula, right? Y equals kx with 2 instead because I just solved it. And now I'm going to find y when x is 9. Well, 2 times 9 is 18. And now I'm done. That's all there is to it. So we'll do a few more of those, and really we'll be done. All right. And this one kind of has that extra wording, so it says y varies directly as, so y equals k times, but this time the square of x. So that's my initial formula. And now we're doing step 2, we're plugging in, and so we get 112. When x is 4, careful, square it, that's 16. Solve, solve, solve. If I divide both sides by 16, let me think about that. 112 divided by 16. Well, that ends up being 7. I now re-plug in the initial formula, or I start writing out the initial formula. And finally, I plug in some new information. Y equals 7 times, I guess, 36. And honestly, whatever that is, work that out. Plug it into your calculator. But whatever that is, that's your final answer. So, really, that one's not too bad. Now, here's one that's probably the most obvious example of direct variation, or one that you've probably encountered. So, Nigel's paycheck, so paycheck, varies directly, sorry, I should use K, as the number of hours worked. And then for 15 hours of work, the pay is $188.25. So $188.25 is the pay for K times 15. Okay, well, all we need to do there is, once again, just do some quick division and solve, and I just can't find my calculator. There it is. So 188.25 divided by 15, I get 12.55 is the hourly rate. So now we know how much Nigel makes per hour. It's $12.55 an hour. Plug that back in. Now that I know the hourly rate, I can figure out how much you get paid no matter how much you work. And so now I want to know how much you get paid when you work 27 hours. And so, times 27, we get 338.85. And that's it, we're done. We've got one more example here, just one, and it's inverse variation. And inverse variation is, I'm going to write it like this, y equals k over x, just to be simplistic for sake of time. So notice that before we were multiplying. Now, notice that k is still in the numerator, right? K is always in the numerator. I should make that look less crazy. But now x is, instead of multiplying to it, it's dividing on the bottom. Besides that, there's really nothing else here. It's the same kind of steps here. So we have pressure varies inversely as the volume. So pressure varies, it's K equals K over the volume. And so there's my initial formula. Let's plug in. If the pressure is 15 pounds per square foot with 4 cubic feet, and if I solve that really quickly, I get K equals 60. Right, I just multiply the 4 over. Now I reset that relationship. You can see how fast this is going. Once you get the concept here, they're really just like 3 quick little simple questions. You just have to see how you're going from one step. So it's initial relationship, substitute given information, solve for K, rewrite with K. Plug in new info. So what's the pressure when it's 1.5 cubic feet? And well, 60 divided by 1.5 is 40. And we are done. So great, we did it. We made it through chapter 7. Joint variation, I'm just going to write this example out, and then I'll let you work through it. If A varies jointly, it just means there's more than one multiplication. So that's all. There's B and C. And great, you just learned joint variation. Besides that, that's the entirety of Chapter 7. So, good luck, happy studying, and I'll see you next time for our next lecture.